first module. The first module of the project is due a week from today. Late! Late! -2. Ouch. All right, so the spinning cube project, I actually have a little simulation that kind of is cool. If I can remember exactly where it's at. Let's see. Should have pulled it up beforehand. So the spinning cube, we are going to be looking at an axis that goes through opposing vertices. And here, some student a few years ago did this simulation of what it's going to look like, which is pretty cool. I don't know what software this is that they did this in, but so that's what the cube's going to look like once we do that spin, which is probably not what you expected, but you know, when you think about having a cube and spinning it, the parts that are probably intuitive are the cone parts. You can imagine the cone parts, but that middle section there turns into a nice smooth arc, which is not what I expected the very first time I did this, when I came across this problem many years ago, and I started working it out. When I was visualizing that middle section, I thought it would be more like an absolute value function in the middle as it was rotating. But it turns out that it's a nice smooth little curve there. And the shape, you can think of it as 3 different solids kind of all glued together. There's a cone on the right, a cone on the left, and then that middle spool-looking thing, kind of like the rim of a bicycle or something. So the very first project, the very first module in the project is to figure out what the equations are for the 2 planes. You can see those 2 planes that kind of subdivide the cone from the middle section and then from the other cone in the other side of the middle section. So that's the first project. The first module of the project is to figure out the equations for those 2 planes. So we'll go through this project, you know, module by module every 2 weeks starting now. This is not my updated version of this. So you do not have to create. I just showed you what it looks like. It's helpful when you're working on it if you just create a little one and have a string and spin it just to sort of see how it works and to see what points are in each of those 2 planes. So it's helpful to do that. You don't have to. So you don't have to build it. You don't have to bring one to class. I've got a model in my office also that I can't bring in here because I can't carry anything, but maybe we'll bring it in here at some point. I'll enlist one of you as a porter, and you can carry it in. But it's helpful to look at the model to sort of help guide you as you're building the different parts of it. So we are going to think of this cube as positioned so that we all come up with the same answers when we're doing this. We're all going to position our cube in the coordinate system in the same way. If we all do it the same, we'll come up with the same equations. So we're imagining our cube sitting in octant number 1. So we're going to position it right there. This is not the best cube, but it's close enough. So we're going to imagine it sitting in octant 1, where this point down here is 1, 1, 0. That point up here is 0, 0, 1. This one over here is 1, 0, 0, etc. So that's how we're going to visualize this. And in the module, I say to put your axis through 1, 0, 0 and 0, 1, 0, 0, 1, 1. So we all are using the same points. So the 2 points that we are putting our axis through, there and there. So our axis will go right through those 2. And then we spin it. And what we have to decide then, there's a couple of ways to find the equations of planes. That's what we're going to talk about today. One of the methods for finding the equation of a plane is called the 3-point method. It's a very simple method. And so if you know 3 points that are in a plane, you can find the equation of that plane very easily. And that's the extent of Module 1 is going to be to find the equations of 2 planes. And so in order to do that, you're going to have to kind of look at the cube and figure out, oh, well, what 3 points are coplanar? Which 3 of the, how many vertices do we have? 8. Which 3 of the vertices are going to be in one plane? Which 3 are going to be in another plane? And if you build it or you look at it carefully or think about it, it will become obvious which 3 points have to be coplanar. And so Mod 1 is just finding the equations of those 2 planes. Questions that you have yet thinking about that? Any questions that come to mind before we actually start finding equations of planes? You guys already know the general equation for a plane. So let's talk about planes. Talk about planes in 3-dimensional space. And planes are going to be found by thinking conceptually about a simple vector equation. And we are going to talk about, every time we talk about a plane, we're going to talk about 2 different vectors. Just like every time we talk about a line, we refer to 2 different vectors. So remember that a line is a curve, and the way we thought of constructing our line was this way. Usually we put a T in front, not after, something like that. You can put it at VT, it doesn't matter. So that's how we constructed lines. We said, find a direction vector for the line, call it V, find some vector that acts like the origin, if you will, and that builds the equation of a line. So for a plane, we're going to also have 2 vectors. We are going to call one of them the normal vector. That's perpendicular to the plane right there. And one of them is going to be a displacement vector in the plane. So, for example, when I look at this point right here, x naught, y naught, z naught, this is a known point that's in the plane, so we know that. Okay, so that's a point that we know is in the plane. And we're going to then construct the equation for the plane by building this vector v that is going to be a displacement vector between the known point and an arbitrary point. Arbitrary point will have coordinates x, y, z. So we're going to build a displacement vector in the plane, a general displacement vector. And this general displacement vector is found by doing tip minus tail. So the tip of the vector is at this unknown x. So we get x minus x naught, y minus y naught, z minus z naught. So this is our direction vector, excuse me, our displacement vector. That displacement vector is in the plane. And what is going to be true, this normal vector, ABC, we'll just use ABC for the normal vector throughout the term. What's going to be true about n and v? What's their relationship? Dot product is 0, right? If we have a vector normal to the plane, right there, any displacement vector down here coming off of x naught, y naught, z naught has to dot to 0 with n. If you build this displacement vector so that it's not perpendicular to n, then those won't dot to 0. So to get all the x, y, z's that are in the plane, you're asking for all displacement vectors off your known point that dot to 0 with the normal vector. So this will generate the equation. What has to be true is that v dot n has to equal 0. So when we dot these together, we get the following equation. So we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So this is the equation of our plane in a standard form. Generally in math, we use the word standard if it reveals information about the geometric object, and we use general if it doesn't reveal information about the object. So the general form of a plane we write as ax plus by plus cz equals d. So that's our general form. Now notice, when we look at this standard form, notice where the constants are. X naught is a constant, y naught is a constant, z naught is a constant, and then a multiplied to x naught, b multiplied to that, c multiplied by that. All those three quantities add up and move it to the other side. That's what becomes d. Right, all those constants combine into d. But notice that a, b, c, a, b, c. So you have never had a clue about the meaning of the coefficients of x, y, and z in the past. So for example, you knew from college algebra that this is a plane. That you knew. But you never talked about what those three numbers mean. Now you know. Now you know that those coefficients are guiding the plane. They're like the slope of a line. So if that's your normal vector, that tells you that the plane is the set of all points that are, forming displacement vectors perpendicular to that. So the normal vector is like a handle, and the plane is, perpendicular to it. Right? So the plane is going to be perpendicular to your normal vector. And so now you know that these three are guiding the points in the plane. They are, the normal vector forms the handle, and then the plane is perpendicular to it. And that you didn't know before. So now you know. Okay, that is what those coefficients mean. That gives us a way to think about where the plane is. All right, so that is where we're at so far. Equation of a plane in general form. Every plane has a normal vector. Every plane has a million normal vectors. You can scale that thing. You can multiply it by -1, right?
Is it always like below?
You can imagine the normal vector. We imagine the normal vector in a way that's just convenient for us. So most of us just imagine the normal vector sticking off the plane like that. But you can imagine it down here. You can imagine it anywhere you want, because vectors are equal if they point in the same direction and have the same length. And the length doesn't even matter. This is a normal vector for the plane. If you scaled it by 5, that would also be a normal vector for the plane. That would also work. So there's no unique normal vector. Doesn't matter. One thing that we like to do typically, when we're asked for a general equation for a plane, we generally like to have the leading coefficient positive. Because if we abide by that, if we say let's all let the leading coefficient be positive, then all of us will come up with the same equation. And we also agree that we divide out any common factors between the constants. If we abide by those two loose rules, positive leading coefficient, cancel common factors, we all have the same equation. So that makes it easier. So those are two convenient guidelines. All right, so there is the general equation right up there. And there is, well, let me read that more. That's the standard equation right there. There's the general equation. So just what we had on the board already. All right, so let's go ahead and build one of these. So I'll always use n, and I'll always use v as the displacement vector in the plane. So in your mind, you should be thinking this. So we've got, let's see, that's not a great plane. Let's see if we have, do we have a parallel? Parallelograms tend to work better when you're trying to envision a plane. All right, so we imagine this normal vector right there. And again, you can imagine it anywhere you want, but that's usually how we imagine it. And this point down here is P. Okay, so that's given. We have that stuff. And now we construct a general displacement vector that's in the plane. So our general displacement vector, what that means is that we're trying to identify all of the x, y, z So that general displacement vector, I'll just always refer to it as V. Just like we do our V as the direction of our line, we always sort of use V and R naught. Here we'll use V and N. So the plane is going to be the set of all x, y, z that satisfy this equation. That will be the plane. So we're going to take our normal vector 1, negative 1, 2. We're going to take our general displacement vector. So we're going to take tip minus tail, so x, y, z, and then subtract off. So we're going to get x minus 1, y minus 0, z plus 3 equals 0. Dot, combine like terms, done. And the more you do this, the more you will probably avoid the step I'm doing right now and start to just combine things all at once. You're going to start to see how everything combines together. So we combine our constants, we get a 5 on the left, which is a minus 5 on the right. So that is the equation of this plane. And it is unique as long as we have a positive coefficient in front and as long as we've canceled out any common factors. Then it's unique.
We got 2z plus 6. Is there a plus sign between the 2 and the z?
Between here?
Yeah.
No, I distributed, so when we do the dot product, this guy is being
Okay.
distributed to that, so that 2 has to be multiplied by both the z and the 3.
I missed that y minus 0 part.
No problem. Any other questions on it as you're looking at it? So that general displacement vector, you're imagining it's spinning around down there for all x, y, z's. You know, x, y, z is a random point in this plane, and we want to get all of the x, y, z that build displacement vectors perpendicular to n. So that will grab all x, y, z that satisfy that condition. So that's the equation of a plane. Very nice. Very nice. Okay, now that we've talked about the general features that a plane has to have, N and V, now let's see if we can figure out what the so-called three-point method will be. So this says we've got 3 points. And any 3 distinct points will form a plane, right? As long as they're not collinear. Any 3 distinct non-collinear points. Right, then you'll have a plane for sure. So what we have to do, what we should be imagining, is a way to figure out what N and V are. So we have these 3 points. Let's draw 3 points in this plane. We'll call them, doesn't matter what we call them, we'll call them P, Q, and R. So that's what we have. What do you think we want to do to figure out what N is?
Use cross product.
Use cross product. So we're going to form 2 displacement vectors. Those displacement vectors will be in the plane. So we have several choices up here. We can displace those 2 guys and then those 2 guys. That would work. A couple other choices also. Does not matter. Yeah, Eric.
Generally for this, you always want to use one of the same point in both cross products, or can you do like A and B and then B and C, or?
So if you did A and B and B and C, you still use B twice then.
Okay.
One of them is going to be used twice. So one of them is going to be thought of as kind of that pivot that you're building a vertex off of.
Okay.
So, and it's not going to matter. We could use this one twice or this one twice or this one twice, and we'll still come up with the exact same equation as long as we divide out common factors and make A positive. So it's not going to matter. So that's a really good question that you could use this one if you wanted. You could go from here to here and then there to there and then cross those 2. And it's going to still work out totally fine. So in our mind, we are imagining that scenario, and our normal vector is going to be the cross product of those 2 vectors. So that normal vector N is going to be PQ cross PR.
Does it matter which way you do the cross product?
Nope. Does not matter. It could be pointing up, pointing down, does not matter. So the only difference that shows up is if you're first component of n is negative, then your a will be negative in the leading coefficient, so then we would divide by -1 to make it positive. Yeah, so it won't matter. Lots of flexibility here. So let's first form PQ. So we'll call that one P, that one Q, that one R. So PQ, we would do Q minus P, so we would go -4, 0, -6. And then PR will be -1 minus 5. -1 minus 5 is -4. No, that's -6. Thank you. That did not seem right. -6. And then 3 minus 3 is 0, and then 1 minus 1 is 0. So there's PR. PQ, PR. Yeah?
Yeah, one thing I've been starting to get in the habit of naming these points A, B, and C, similar to how I would name vertices on a triangle. Would that be a problem?
It's totally fine. I would using capitals, I'm
Yeah, that's-
assuming.
yeah, that's
Yeah,
great.
totally fine. Because normally we'll use little ABC in this class to represent the coefficients of the plane.
All right, so then I
But
probably
if you
shouldn't-
lose capital A, B, and C, it's fine.
So I probably shouldn't use lowercase a, b, and c to refer to the displacement vector.
Yeah, A, B, and C will always refer to those coefficients of n. So,
Yeah, okay.
you know, those guys right there.
Right.
All right, so then we do a crisscross. And we get, let's see, 0. Oh, 0 is 0 minus 0. That I can do. And then we get 36.
Should the 6 on the bottom be positive?
Let's check. And then 0. That one right there?
Yeah.
So PR, we would do R, so we always do the tip minus the tail.
Okay.
So it's R minus P, so it will be negative. So R minus P will be negative. All right, so there's our normal vector, or a normal vector.
Do you have to switch the signs on the
Let's see.
You did.
So cross out the middle. The main diagonal is 0. The other diagonal is positive 36, so we get negative 36, and we switch and get positive 36. Although again, it won't. In this case, it won't matter. Yeah.
Because you said you had like infinite normal vectors, does
Yep.
that mean it doesn't matter what order you cross your vectors you found in?
Yes.
Okay, cool.
Exactly. So yeah, it's not going to matter. You could do P, you could do QP cross RP, you could do the whole 6 choices. And then, now, do you think the length of the normal vector is important in figuring out n dot b equals 0?
Probably not.
No. So why not? We could use n equal 0, 1, 0.
Could you just divide everything by
Divide everything by
36?
36. Yep. So now, the equation of our plane, we have to have n dot v equal to 0. So n we just found to be 0, 1, 0. V is our general displacement vector. So we have not drawn v yet up here, and maybe it gets a little messy trying to throw it in there. But v is just a general displacement vector in the plane, right there. And the tip of that we just imagine being x, y, z.
So it has to touch the outside of the plane.
No. That's coincidence.
Then why can't we use R or Q?
You can. Oh, what? No, you can't. Sorry. You can't. You can't. You can. At least, I'm not, if I understand your question correctly. So the general displacement vector is between n and the point that we're imagining that displacement vector at. Right?
Right.
So that general displacement vector is coming off of n. Now your question was, let me see if I know what your question is. So I would build this as x minus p was 531. So that's how I would build that general displacement vector off p. So it's x, y, z minus the point
It's
right
minus
there.
a point.
Minus that point. That's the general displacement vector. Now, that said, could we do what you suggested? Could we conceptually say, oh, let's move this over to here, and let's do x minus 1, y minus 3, z minus 1. Would that work? That would also work. That would just be creating a slightly different point displacement vector, but it would still be in the plane. So it doesn't matter in the big picture. Now, if we want to do it just so that it matches what this general sketch is, then we would certainly use P just because that matches our sketch. But in the long run, it's not going to matter. So you can pick any point you want as your pivot point, as your vertex. Okay, so then we dot these together and we get our equation. Zeros, everything, we end up with y minus 3 equals 0, so we end up with a nice simple plane, y equals 3. When you get a plane that simple, you have to think, was there another way? In general, there's not another way, but when you get something quite so simple, you look up here, and what do you notice that's true about those 3 points?
They all have the number 3 as their
They all share 3 as the y value, so you know that the plane has to be y equals 3. So if you had foresight, which you haven't developed yet because we just started that, but you can observe that you're dealing with 3 points that are in the plane y equals 3. So that has to be the plane. All right? They all share 3.
Does that happen often?
No.
Okay.
No. Nope. All right, any question on the concept there? N dot V is 0. N dot V. Okay, so just some terminology. If we have 2 distinct planes, we now know how to find their normal vectors. Yeah?
Just a quick question, is there any way you could ever get all the variables to cancel out? And you just would have 0 and no plane?
Well, then most likely what's happening is that the 3 points are collinear. Because you have, in order to get a plane, you have to end up with 1 letter. This is the simplest it could boil down to, is if they're all in a plane that's parallel to a coordinate plane.
Okay.
Yeah. So if all the letters disappear, then you could have a contradiction, or you could have, you have something's going on, so you probably have 3 collinear points.
Right.
Probably what's happening. If we have distinct planes, we have 2 options here. They could either be parallel, or they could be, or they could intersect. Those are the 2 possibilities. So if they're parallel, that just means that the normal vectors are parallel. If you have 2 distinct planes, so they're not the same plane, 2 distinct planes, if the normal vectors are parallel, the planes are parallel. Similarly, if you have 2 planes that intersect, that line of intersection is going to be, oh, actually, let me restate what I was about to say. I was about to state someone that's more general. Here they're talking specifically about perpendicular planes. What's true about 2 perpendicular planes? Their dot product for their normal vectors has to be 0. Yeah, so I was going to say something slightly more general, which I will say right now. So if the planes are perpendicular, the dot product is 0. But if they're not perpendicular, if they just intersect at a smaller angle than 90 degrees, what's true about the direction vector for the line of intersection? Cross product. If you take the cross product of n1 and n2, that is going to be equal to the direction vector for that line right there, correct? You don't believe me? If you imagine this wall, I know you can do that, and you can imagine this wall, there's the line of intersection. So if you take that normal vector and that normal vector and cross them, right, it's going to point in the direction of the crease, the line of intersection. Always. Always. And when is the cross product equal to 0? The cross product is equal to 0 when...
They're the same thing.
So cross product is measuring the, so yeah, there's that parallel, like you said, parallel. Then the normal vectors are parallel. Yeah, good point. So if you do the cross product, then you know you're in, and you get 0, you know you're in this situation. Okay, so let's try this one. Parallel planes. You guys try this one. So you want to find a plane that's parallel to plane Q that contains the point P naught, 1, 2, 0. Ready, go. So you're finding the equation of the plane. What two things do you need for the equation of a plane?
Dot product of N and V has to be
N dot V has to be 0. So you have to figure out an N and you have to figure out a V. Anytime you want the equation of a plane, this is where you start. N dot V is 0. So figure out an N, figure out a V, and then dot them together. Dot.
Do you have to use the normal vector?
Yep.
Okay.
Right? If their plane is parallel to plane Q, they have the same normal. Right?
Wow.
If you have parallel. Oh, brother. I'm coming over here. Safer back here.
Safer.
Safer back here. So a normal vector, you're going to choose your normal vector to be. Yeah, 1, -5, -2.
Wait, I'm dotting.
And then your displacement vector is just off that point. Yep. And then combine your like terms and put the constant on the right.
How do we find it?
Yep, x minus 1. That was 1, and -5 times y minus 2.
So that's supposed to be.
Oh, this is right.
Yeah, that one's a 1. Right, that one's a 1. And then that's -2 times.
Oh, it might be.
Yes. That's good. Makes sense? Yep, that's your n, and so now your displacement vector is off of that point. So x minus 1 is y minus 2, z minus 0. So anytime you've got a point that's in your plane, you can build that displacement vector really simply by doing exactly that. Yeah. Pick again. I'm using invisible ink. All right, so normal vector. Somebody tell me the coordinates or components of the normal vector.
1, -5,
1, -5,
-2.
-2. So normal vector, displacement vector, x minus 1, y minus 2, z minus 0. So then you dot them together and get 0. So you're going to have x minus 1, I'll put it all out, 1 times x minus 1, minus 5 times y minus 2, minus 2 times z minus 0. That's all 0.
Yep.
So x minus 5y minus 2z. Then we just have to put the constants on the right. So we have a -1 and a +10. So that's so it should be 9 over here.
Negative
9.
Plus
Oh yeah, -9 over there. Somebody had 11 back there?
Yeah.
Yeah, it makes, yeah, okay. Should be -9.
Yeah.
-9. -9. Wow, so cool.
It's hard to get the old mouses turning after Monday.
Is it? You still feel like you have exam blues?
I
Yeah.
still have it.
Exam aftermath?
So that -1 you have in the equation of just the plane Q, does that not affect the intersection of the planes, or
Say that again, this?
that one there? And
That one right there?
Come into play more?
Well, it comes into play in the sense that notice that the left side of this and the left side of this are the same, but they have a different constant. So that means they have a normal vector that's the same, but there's distance between them.
But it could have been like 5 and you would still end up with the same equation, or?
Oh, yes.
So
Yeah.
it doesn't matter what that constant is?
No, yeah, it doesn't matter at all. Right, good point. So do you understand the question? So looking at that constant right there, he's saying that we never use that anywhere. And the answer is, yeah, we never use it. We don't need to. Right? If we have this plane and we build a parallel plane that goes through 1, 2, 0, there it is. Well, that's the same plane that would be parallel to this plane that goes through 1, 2, 0. Right? It's not going to matter. Now, how far apart are those two planes?
9 units.
8.
10 units?
1, 2, 3.
They are not 10 units apart.
Okay.
They are not 10 units apart. If you had the plane z equals 1 and z equals -9, those planes would be 10 units apart. Those planes are not 10 units apart. So if you wanted to do some extra credit, oh wait, wrong group. If you wanted to do, so if you did have parallel planes, it's a very fascinating question, how far apart they are. Let's suppose we pick a point in one and a point in the other. So those are just two parallel planes. If we wanted to know how far apart they are, what we would be trying to do is figuring out this perpendicular distance. That would be defined as the distance between the two.
Would you do a projection?
Boom! Oh, that is so awesome.
I'll take that extra credit on my test score, please.
Can you apply that to question number 5 on the test? Okay, so there is PQ right there, and I am going to very strategically place the normal vector. I'm just going to put it right there. We don't know how long it is. Doesn't matter how long it is. Right there. Very strategic. So we can visualize if we, this distance, I'm just going to move it over there. There. Can you see that D is equal to the magnitude of the scalar component of the projection of PQ onto N? All right, if we're projecting PQ onto N, remember that when we project, if the angle is, you can get a negative for that scalar component depending on whether you're dealing with an obtuse angle or an acute angle. And so you can imagine PQ being skewed this way where you'd have an obtuse angle. So that could be negative, so that's why we take the absolute value. So this is going to be, what is this going to be? Absolute value of N dot PQ divided by the length of the N. That will give you the distance between two parallel planes. So we already know what the normal vector is. We just have to figure out this displacement vector between the two planes and then find that absolute value of the scalar component. That would give it to us. N dot PQ divided by N. All right, so great question. Any questions on this idea before we go on to another problem?
So this is going to be something that's going to be on the test?
Finding the equation of planes?
No.
Yes.
The distance.
Finding the distance between parallel planes. For some reason, this book does not emphasize that, so it won't be on the test.
Much to your disappointment.
Yeah. Feels like such an important question.
Yeah.
Well, we obviously all asked.
I could put it on as extra credit.
Do
you
it.
please
I mean,
have
it
our
wouldn't be
safe
the worst.
grace be finding the distance
Finding the
between
distance between two planes. Or, yeah, I might do that. I might do that. All right, let's keep going. So intersecting planes here. Find the equation of the line of intersection of the planes the planes Q and R. All right, you guys try that. See if you can, without having given you a specific example, let's see if you can figure it out. We talked about all these concepts, so you should be able to reason it out in your head.
My reasoning like button is out of order.
Out of order.
Blinking. Yeah. So always ask yourself what you need. So if you're trying to find the equation of a line, what do you need for the equation of a line?
A direction vector.
So it's equivalent to the y equals mx plus b, but when we're dealing with a line in three-dimensional space, remember that we're dealing with this equation.
You need an R naught and a V vector.
Yep. R naught and v, that's what you're trying to find. And you'll find a normal for each of these planes. Is anyone clear on how you're going to find your v? I see some clarity there. Exactly. Is anyone not sure how to find V? So what operation are you using to find V? Cross product.
Multiplying by 4.
Exactly what we talked about here. So if we have a normal here and a normal here, if we cross them, we're going to get the direction for the crease. Right? And so two normals crossed will give you the direction of the line of intersection.
So can we, sort of like when we're building a line, can we choose either one to be our
No.
initial point? Does it have to be the,
No.
no.
So the,
Wrong.
this is the hard. This is the hard part.
Okay.
So if you want to find a, you can use any point on that line of intersection.
Okay.
The question is, how do you find that? You can randomly pick a point on here. You can randomly pick a point on there, but that doesn't make it on the intersection.
Right.
So how do you find the intersection of two geometric objects? What do you do with their equations? Yeah. Yeah. Simultaneously solve.
Oh, so you set those equal?
Setting equal, maybe that's not exactly the right terminology. What
You
we
set the-
solve the system.
Oh. Oh.
I think it is setting it equal to each other because
Yeah.
because you're solving for the points, for the set of points that
You're
are the same for
setting
both.
you're setting one coordinate equal. So let me explain that. Okay, so if we have two planes here and we want to know where they intersect, we want to know a relationship between the coordinates of the points on that line of intersection. So here, so normally what you would do is set up a system. In college algebra, this was a system where you found the intersection of two planes. You did do this in college algebra most likely, where you had an infinite number of solutions, because that line is representing an infinite number of points that are shared by the two planes. So the simplest way in this case is if we add these together. So if I eliminate y, conceptually what I'm saying is let's consider the points on the line of intersection where the y values are the same for the two planes. If we eliminate y, we're saying the y value is the same for the two planes. Then this gives us a relationship between the z and the x coordinates. So now we can find a solution. So somebody give me an x value.
1.
So if we pick x to be 1, what does that tell us z has to be? 2. What does that mean y has to be? 0? That doesn't seem right to me.
Because we deleted it.
Did you plug it in here?
No.
1 plus 2 is 3. Subtract 3 from both sides, it has to be -4, doesn't it?
I was like 4 off.
You're close. Close. Does everybody follow that? So conceptually what we did was say, oh, let's assume we're going to pick the point where the y values are the same. So we eliminate y. Then we get a relationship between x and z. Then we can pick an x. If we just need one point on the line of intersection, pick an x. You can pick any x value you want. There's going to be a point on that line that has, you know, whatever x value you pick, unless it happens to be a very interesting line of intersection. You know, like if it's parallel to an axis or something, then maybe you'll notice something funny. So we can pick that. So somebody give me another point. Let's show that it does not matter which point we pick. What's another point? What x value?
20.
No!
720,000.
0 is a great choice. We plug in 0, we get 0, -1, 0. So let's show that it's not going to matter what point we pick. So those are both points that are on the line of intersection. There's an infinite number of them. One of them does have an x value of 20. We're not going to use that one, though. You can use that one, Will. All right, so now we need to build our line. So the line, we're going to use, we're going to create a vector that points to that first point, P1. And then we got our direction vector right there. No, it's over there. Where did I cross them? Oh, I didn't even cross them yet. I didn't even cross those yet. So we have to get our direction vector up here. I know some of you guys crossed them already.
1.
132 is what I've got.
I got 1 -32.
So,
Oh, I forgot to swap this up.
so the direction vector for the line, tell me it again.
1, -3, 2.
1, -3, 2. So that was formed by crossing.
I got 1, 3, 2.
You got 1, 3.
I got 1, 3, 2. But did I switch it?
-2 minus 1.
All right, let me double check since I hear a little bit. So we cross out the first column, we get -1 plus 2. That's that. Cross out the middle, we get -2 minus 1, which is -3. Cross out that, we get 1. I agree with that.
We switched this.
1, -3, 2. So that is now the direction, 1, -3, 2. Multiply that by t. So there is the equation for our line of intersection. So 1 plus t, comma, minus 4, minus 3t, comma, 2, plus 2t. All right. So that definitely works. Now, or we could do it the other way with the other point. We kind of see what the pattern is going to be. The only difference is that we are going to have this. We're going to have t. We're going to have minus 1 minus 3t. And you're going to have, what, 2t for the last one? Either of those works. As a teacher, this sucks. Both of those are equally valid, right?
As a teacher, this sucks.
Because now I don't know what point you chose, right?
So give us.
So so maybe I should give you the point. So when you look at this, we would have to how could we convince ourselves that those two lines are identical?
Set them equal to each other.
We know they're both lines, so we could show that they both can. It's 2 points determine a line. So we could find 2 points on this line, and then verify that those same 2 points are on this line. Right, we could do that. Or we could even probably more easily, if we look at this first equation here that we generated from that point, can we find a t value that generates this other point? What t value would we use to generate this point? -1. So this first line was generated with 0.1, and if we let t be -1, we will get this point. So that also does it for us. And if we look at this line, we say, hey, what t value should we use here? And if we plug in 1 for the t value here, we've constructed the line with that point, but this point is on it. So that's essentially showing that there's 2 points, 2 common points on both lines.
When you have something like intersecting with a plane, are you always looking for like the cross section like being kind of projected onto that plane? Like let's say you didn't have 2 planes intersecting, like let's say you had a sphere and a plane, would you be looking for like an equation of a circle
Yes.
on the plane then? Okay.
Or, yeah, yes.
Okay, does this method still work for that or is it
Yes.
Oh, cool.
Yep. Yeah, we'll still use, regardless of what the geometric objects are, we will do this same kind of thing. We will substitute one into the other. So usually when we say simultaneously solve, that's what we mean, where we plug one into the other. Sometimes we say set them equal to each other, but we're essentially plugging one into the other to see what's left over, see what they share, to see what the common points are. So either one of those is great. Either one of those works. Whoops. Either one of those is totally fine. But there are more than one solution. There is more than one solution. All right.
Can I ask something?
Yeah, of course.
So what was the, like we solved for y when we had the system,
Uh-huh.
and then we had z equals 2x, and that's just to find,
So this tells us that if you imagine all the points on that line,
yeah,
that tells us that the relationship between the z and the x coordinate is always that.
okay.
That every single point on that line of intersection, z is going to be twice whatever the x coordinate is.
Okay.
If we wanted to figure out the relationship between z and y, we would eliminate the x. So if we wanted to, we could come up here and say, hey, let's ditch x instead of ditching y. If we subtract these equations, the x's will go away. So we would end up with minus 2y minus 3z equals 2, I believe, if we subtracted correctly. Everyone agree with that? Then we would say that 3z is equal to minus 2y minus 2.
It's
and
just gonna
then
be your point.
z is equal to minus 2/3. Weird. Z is equal to minus 2/3 y minus 2/3. So that's how all the z and y coordinates are related on that line of intersection. Anytime we know what the y value is, the z value is related in that way
That just gives us the points where they intersect, and then we can plug it back into the system.
to get x.
Okay.
So here, if you pick z equals 3, or whatever you want, or y, excuse me, if you pick y equals whatever you want, that would determine z, then we plug those both back into one of the original equations, and that would give us x. Yeah. Is there another homework?
Yeah, so I was wondering something. So you said one of the main stipulants is the fact that n dot v has to equal 0.
Right.
Can't we just say v equals 0?
That
v
is
equals 0, 0, 0, and then at all points, dot
that
y
is
0.
one solution to that equation, right? But but that's not, so if the goal is to find the equation of the plane, not just so if you wanted to find, so you're basically asking about the solutions to wherever that equation is, n dot v is 0.
Yeah.
So if you want the solutions to that is absolutely true that if v is equal to the 0 vector, that would be a solution to this. Absolutely.
Right.
But that's not all solutions, that's just the degenerate solution. Right? And so what is visually what is happening when you're doing what you just said? Where is v equals 0? V equals 0 is that point right there.
Yeah.
So that is one point that is on the plane. But we want all the x, y, z's that are going to satisfy that. So this will just be one solution, but not all.
Okay.
So we want all infinite points, all infinite solutions. All right, so let's define a cylinder, since you guys don't know what a cylinder is.
You don't?
Nope, I don't think so. Most people that come into Calc 3 think they know what a cylinder is, and then they see this definition, and that's a cylinder. And you say, oh no.
It's an unrolled.
Yeah, exactly. So the cylinder you're used to dealing with is a right circular cylinder. But in general, a cylinder is defined by two things. We have a curve. That's called the generating curve. So for a right circular cylinder, the generating curve is a circle. And then you choose a line, and that line goes through your curve. Doesn't have to be perpendicular to it. With a right circular cylinder, you choose a circle as your generating curve, and you choose a line, they call it a ruling. Choose the rulings to be perpendicular to that circle, and it builds a right circular cylinder. But in general, if you peel apart the components, you have a curve, generating curve, you have a ruling, and then you form all parallel lines to L, and that forms a cylinder. So that's the general definition of a cylinder. Generating curve, ruling, and then all the parallel lines to the ruling that you pick. So the only condition up here is that we've got a given curve, so that's our generating curve, and a line L that's not in the exact same plane. Does that make sense? Like if you had a generating curve of a circle, that's in a plane. You can't have your ruling be in that same plane as the circle, or you're not going to get anything. Everyone follow that? So if you have your circle, the ruling has to be out of the plane that the circle's in, so that you get something that's not degenerate. Okay, so that's a cylinder. Here's another cylinder. Here we have a parabola as the generating curve, and we're choosing rulings that are perpendicular to the YZ plane. So that's another cylinder.
I don't quite get the part about all the lines parallel to L.
Mm-hmm.
Like, who's to say that they're parallel to L like that? Why can't they be parallel to L in some other direction?
They have to be parallel to L and go through the curve.
Can't they still do that? If you just like rotated each line generated by
No, they-
20 degrees. And
So
how
here is
long
the
that
main
was
ruling is the x-axis.
Oh,
And so if we want all lines parallel that go through the red curve there, as soon as we move here, that's not through the red curve. That's not through the red curve.
No, that's not what I mean. Like, if you were to rotate each line using L as like the axis of rotation.
Yeah, I know. Yeah, so you're talking basically about taking, if you imagine a right circular cylinder and just skewing it.
Yeah, sort of.
Yeah, you can do that.
Is that still a cylinder?
Yeah.
I don't like that.
Oh, yes. Finally, a math class gets to make you unhappy. Yes. In a psychological way. Okay, so yeah, that is a cylinder. Those are all cylinders.
I've never been bullied geometrically before.
Bullied geometrically. You didn't even know it was possible. All right, so here we have a parabola as the generating curve. That parabola is sitting in the YZ plane. Okay, so that parabola is sitting in the YZ plane. One really simple way to recognize a cylinder is if one of the letters is missing. If one of the letters is missing, then you have a cylinder. Right? Because this tells us the relationship between z and y. This says that z has to equal y squared no matter what. So if you look at the points on this parabola, you look at any one of those points, z is going to be equal to y squared. What does it tell you about x? Nothing. So that means there's no restriction on x. That means that there's no restriction, so that means that the, done this in a while. Where is my, where did, oh, there it is. It's the cloner. So that means that you could imagine that there or there, all of these are solutions to this equation because there's no restriction on the x. So the first parabola I drew in the YZ plane was where the x values were 0. But this equation doesn't restrict x. So x could be 0, could be 1, it could be 2, it could be 3, it could be 4, it could be pi.
Does that form here?
So that forms our whole cylinder. So if we connect all these together or imagine them connected together, we have that cylinder. So another way to think about a cylinder is that you have your generating curve and you extrude it parallel to the ruling. So in this case, we're imagining the x-axis as the ruling because x is missing. We extrude it in the x direction. We pull it in the x direction. And that's going to build our cylinder. So a right circular cylinder, you can imagine a circle and you pull it perpendicular to the plane that the cylinder is in, and that builds your right circular cylinder. So identify the coordinate axis to which the cylinder is parallel. What axis is the cylinder parallel to?
For cylinders, are we always going to work with one of the axes being the ruling
For
axis?
us, 99% of the time,
Okay.
if the ruling is not parallel, if it's not parallel to one of the axes, it's really complicated.
Okay.
Yeah. So they may do a couple of problems where they do that, but 99% of the time, for us, we'll see, oh, x is missing, so we pull in the x direction. Oh, y is missing, so we pull in the y direction. Z is missing, we pull in the z direction. That's going to be 99% of the time.
Do you consider the folks at MML as part of the us group?
Yes.
Okay, good.
Yeah, they're not going to ask you for cylinders where you have at least nothing crazy. But 99% of the time, the ruling will be parallel to an axis.
So whichever letter is missing, that's the axis it's parallel to.
Mm-hmm. Yep. Yep. All right, let's take our 10-minute break.
I'm gonna
We'll go jump around in 12-2. This is, okay, this is a surface. It is called a paraboloid. And what we want to do is talk about the 6 quadric surfaces. And we need some way to figure out what these quadric surfaces look like. And so what we're going to do is categorize our 6 quadric surfaces, but then we're going to look at these things called the traces, because if somebody throws you an equation and says it's a quadric surface, you need to be able to identify which quadric surface it is. And the way that we do that is through traces. So if we look at this quadric surface here, we see that the intersection with the xy plane here is a circle. We see that the intersection with the xz plane is a parabola, and over there we have another parabola. And so what we'll be able to do is take the traces and sort of imagine what the whole surface is. So that is a paraboloid, and the traces are simply the intersections with the xy plane, the yz plane, and the xz plane. So everyone can see those traces? So the trace is a curve in one of the coordinate planes. So quadric surfaces are kind of analogous to the curves in college algebra. What are those things called? The ellipse, the parabola, and the hyperbola?
Oh, conics.
Conics. So the quadrics are analogous to the conics. In college algebra, you had 3 conics. Here we have 6 quadrics. And so, let's see. This right here is going to be one of them. This is called a hyperboloid. Let's skip a page. Did I? Okay, yeah, that's coming down there. So this is going to be a hyperboloid of 1 sheet. We're going to see that there's 2 different types of hyperboloids. A hyperboloid of 1 sheet and a hyperboloid of 2 sheets. So let's just find the traces here first. So to find the xy trace, we eliminate z. We just want to know what's going on in the xy planes. So for the xy trace, we're just compressing our surface down onto the xy plane by eliminating the z coordinate. We're going to let z be 0. So the xy trace is going to be whatever we get when we let z be 0. And this is an ellipse. All right, let's go for the yz trace. The yz trace, we're going to let x be 0. So we end up with y squared over 9 minus z squared equals 1. That's a hyperbola. And the last trace, the xz trace, we are going to get, let's see, we're going to let y be 0 now. So we're going to get x squared over 25, and this is also a hyperbola. Also a hyperbola. So 2 hyperbolas and an ellipse. This is going to be a classic hyperboloid of 1 sheet. Hyperboloids of 1 sheet look like radioactive, the power plant, those towers, kind of like a nuclear tower, power plant tower.
Could you remind me of the equation of a hyperbola?
Hyperbola.
Two-dimensional space again. How do you know it's a hyperbola?
A difference of squares being 1. Difference of squares being 1 is a hyperbola. Sum of squares being 1 is an ellipse. And then we can always go. So I mentioned this program to you one day, this GeoGebra program. If you go to geogebra.org and click on 3D graphing, you can graph all sorts of whatever you want here. What was this equation? Did someone write it down?
X squared over 25, my square squared
Hold on,
over.
it's not.
He's just ready.
It froze up. Let's see. We're gonna come back to life.
And then when you want the hyperbole of it, you want us to just really exaggerate everything about it, right?
Exactly.
Okay.
X squared over 25
Plus minus y squared over 9.
minus y squared over 9
No, it's plus y squared.
Oh, it is?
plus y squared over 9
Minus c squared
minus z to the 2
equals
1.
Boom.
I don't like
Thanks!
Everyone.
It's turn. So,
Yeah, like, oh,
so
I
you can
see.
see the waist of it right there.
Okay.
That's pretty sweet, actually.
So
Like a
now watch this.
volcano.
This is super cool. So if we click there, oh no, that's not how we do it. Let's see. There's a cool thing you can do with the axes here. I think you hold the control button down, and then you can grab an. Let's see.
Okay.
Maybe grab like the arrow at the head of the axes.
I don't think you have to go all the way up there. I thought it was control. Maybe it's shift. I don't know. You can grab the axes. I just can't remember what the command is.
So make it even look even more like a wormhole.
Although it's kind of freezing right now. I can't even move it right now.
It's
Right.
upset.
Explaining it.
Yeah, that's probably, let's delete it. So if we go with something simpler, that probably is just a little bit rough for it. So if we have something like that, so this is going to be a paraboloid. I thought it was here. Let's see. Yeah. Oh, let's see, so that's, yeah, I don't know, there's some commands that you can use to play with it though. But that's always an option, is to graph over in GeoGebra just to get a sense of what it is if you're not 100% sure. Okay, so let's take a look at our 6 quadric surfaces and talk about the traces for each. The first one is an ellipsoid. And can you see that all the traces are ellipses? And when we say ellipse, circle is an ellipse also. So one of the, most of the times for an ellipse, you have it oblong and one direction is a circle though. So in this case, it looks like there's a circle in the XZ plane. So the way that you try to identify these quadrics, once you sort of see what the shapes are, then you can write out those traces like I just did, or you can kind of cover up in your mind and think, oh, ellipse, ellipse, ellipse. Must be an ellipsoid. So you kind of get into the habit of, once you're clear on what the traces are, so here is a paraboloid that's not shifted, it's sitting on the XY plane. We have 2 parabolas, and what's the trace with the XY plane? Trace with the XY plane is just a dot, right? Because it's resting on the XY plane. So it's just a single point. So if you have a paraboloid that's not shifted around somewhere, you're going to have a parabola, and a point. Parabola, parabola, point. Next one is the hyperboloid of one sheet. It's one that looks like the nuclear tower. And the traces, like we just saw, circle, hyperbola, hyperbola. So you've got hyperbolas in the XZ plane and the YZ plane, but then in the XY plane you have a circle or an ellipse. So they tell us right over here what the different traces are. That's the other hyperboloid, hyperboloid of 2 sheets. So this one, let's look carefully. So certainly we see the 2 hyperbolas, right? We see the hyperbola in the, yeah, that's going to help. So we see the hyperbola in the XY plane, in the XZ plane, and in the YZ plane. We see those hyperbolas. But what's the intersection with the XY plane? Empty set. So if you get 2 hyperbolas and an ellipse, you know it's a hyperboloid of 1 sheet. If you get 2 hyperbolas and empty set, you know it's the hyperboloid of 2 sheets. Hyperboloid. And then the last 2, the cone. In Calc 3, when we talk about a quadric surface cone, it means there's 2 sides to it. It goes up and down forever. So both sides are appearing for a quadric surface cone. And what do you think the traces are? Let's see. Trace with the XY plane. Single point. Right? So we've had the paraboloid have a single point in the XY plane, and now we have the cone has a single point in the XY plane. But then what about the other 2 traces? Don't you get an X for both of them? Right, you get 2 X's. They call it intersecting lines. And then we have the saddle surface, not to be confused with the monkey saddle surface. The monkey saddle surface has 3 dips, so there's a place for both legs and the tail. This only has 2 dips, so they call it just a saddle, not the monkey saddle. But there is a monkey saddle if you pay attention. And the traces here, you will have a parabola that opens up, a parabola that opens down, And then what about the trace in the xy plane? What if you let z equal 0? So let's imagine the simplest possible hyperbolic paraboloid, the simplest possible saddle. If we let z be 0, so this is the xy trace, what is that graph? X squared minus y squared equals 0.
A line?
Say it again.
A line?
More than one line, though. So, do you agree it's going to be more than one? How many? Two. It's going to be 2 lines.
Y equals X.
And y equals negative x.
Oh yeah, because they're both squared.
Yeah, so we'll get that. So to convince yourself, you could factor this into x minus y times x plus y. So you would get y equals plus or minus x. So you get intersecting lines again. So if you look up at that saddle, you can kind of see it. So down here, they have the dashed lines there where the surface is meeting the xy plane. So there's going to be a pair of intersecting lines. Would be your trace. This one's easy to identify, though. If you get an up parabola and a down parabola, you're going to have a hyperbolic paraboloid.
Yeah, what was the equation for the elliptic cone again?
For the cone,
Yeah.
so for the cone, oh wait, that was the top of this one. So the cone, if you look at your traces, if you let y be 0, if that goes away, you get x squared equals z squared, so you get the same thing, you get a pair of lines. And if you let the first coordinate be 0, you get y equals plus or minus z when you take the square root, so you get pair of lines, and when you let that one be 0, you get just a point. X squared plus y squared equals 0 is a point. All right, so let's see, how many more slides do we have here? We still have, this is our last one. Okay, good. 2 problems here. All right, yeah, we'll be good. Okay, so we want to identify this quadric surface. So this is typical situation. We might not be able to just look at it and recognize it. So we can deal with traces, or sometimes we can put this in a different form. The thing that jumps out at me right away is that, oh, there's x's in more than one place. So this looks like something that has a shift in it. You know, like when we shift a circle, all of a sudden we have a linear term in there, a 2x or 4x or something. So let's complete the square and see if we get to something we're familiar with. So we have x squared plus 2x. The y's and the z's are totally fine. And what are we going to add for our completing the square term? 1, both sides, complete the square. Okay, so we have a couple of ways to deal with this. First off, we notice that it is shifted. There's a center, -1, 0, 0. And now this one is one of the simpler surfaces, so we probably recognize that it is an ellipsoid. Everything's squared to 1. The sum of 3 squares being 1. That's going to be an ellipsoid. Now, if you want to use the trace method, my recommendation is to take away the shift, right? If you take away the shift, that's where we focused on our traces with our quadrics. Get rid of the shift. So this is, if we boil this down to what the non-shifted equation, this would be the non-shifted. Unshifted. So that's where I would look for traces. I would look for traces with the unshifted one. It's just simpler. So if we eliminate the x, ellipse, eliminate the y, ellipse, eliminate the z, ellipse. So all traces are ellipses.
Wait, no, if you eliminate the z, don't you get a circle?
Yeah, that's an ellipse.
Oh, yeah.
A circle is just a special ellipse where both radii are the same. Yeah. And so all traces are ellipses, so therefore we have an ellipsoid.
And pretty much the idea is for us to memorize all of these different surfaces.
Yep, that's the idea.
Fun.
No card time! Yep, so there's only 6.
Yeah, it could be worse.
Could be worse.
At least you don't
Yeah,
have
when we get into, so in 2-dimensional space with conics, we had 3. In 3-dimensional space, we have 6. So when we start going into 4-dimensional space, we'll probably have more. I am kidding you. Yeah, we will not graph in 4-dimensional space. You might do that at Mines. Might drive you crazy. Bad jokes. Oh boy. Okay, so we want to identify what this is. Now, with the quadric surfaces all had all 3 letters. So this is not a quadric surface. This has something missing. So what do you think this surface would be called?
Trace.
Yeah, cylinder. Exactly. So spot on. Oh boy. All right, so this is a cylinder. And it's going to be extruded parallel to the x-axis. So in the YZ plane, we're dealing with a hyperbola. So if we were to put this in standard form, we'd be dealing with that. Let's graph a hyperbola since it's probably been a while. Okay, so to graph a hyperbola, let z be 0. And you're going to get y equals plus or minus root 2. So we'll just guesstimate where root 2 would be.
Very helpful since we haven't defined our scales.
Right there. That's root 2. That's my scale.
Yep.
Very easy. And then we let y be 0. And we get z equals. Nope. Can a hyperbola have intercepts on both axes? No. So there's going to be no z intercepts. So the hyperbola is going to be something like, it's going to go out that way and down below over there. And then we have to extrude it, so it's going to be extruded parallel to us, so it's going to come kind of like that. Yeah, we won't be asking you to draw many of these.
Whoa.
Because that's too hard.
So are those 2 cylinders?
It's still considered a cylindrical surface, but it is a disconnected cylindrical surface.
So it's like if you turned them around, maybe it's
Maybe. Yeah, they call it a cylindrical surface, even though there's 2 parts to it. It's a compound region, disconnected region. There's a whole bunch of math on connected surfaces and disconnected surfaces.
There's a whole bunch of math on everything.
There's a whole bunch of math on a whole bunch of surfaces. Okay, so you get the idea. Let's do one more here. Let's suppose you figure out what this one is. Let's try that. Does that make even? Yeah, that makes sense. Yeah, that makes sense. Try that and just see. Maybe some of you see it instantly, but just see. So identify what quadric this is.
Is this an elliptic paralloid?
Say that again.
An elliptic paralloid?
Paraboloid?
That one.
Yes. Yes, it is a paraboloid. That's
Is that
the second simplest one.
z is square, not square?
Right. So if we look at the this trace, we get that, which is just a point. If we look at the yz trace and solve, we get z equals y squared. So that's a parabola. And the other trace, xz, so we're going to let y be 0, we get z equals x squared. We also get a parabola. So this is going to be a paraboloid.
It's an elliptic if the z squared?
If this, so here, if this was an ellipse instead of a circle, I mean, we usually just say paraboloid. It could mean an elliptic paraboloid or a circular paraboloid. It doesn't really, they usually don't distinguish. They always call it elliptic paraboloid here.
Oh, yeah.
Yeah.
So are we like always gonna be solving like the second variable in like the plane? So for x, y, we're gonna solve for y.
Mhm.
So it would be y equals 0 and same with
Yes. Yeah, that's a good way to do it because that gives you a sense if you're in the xy plane, you know how functions work, so we usually solve for y. I mean, if it's a conic, you don't have to.
Right.
You know, if it's x squared plus y squared equals 4, you don't have to. Question? No question. No question. All right, let's go to the next section. Talk a little bit more about functions. Functions. Oh, you have a question?
Oh no, I was just saying that I said OCD strikes again. I finished graphing the previous one. By the time you finished like explaining the one after it.
Nice graph.
Thank you. It'll serve me well.
It'll serve you very well. All right, let's talk about something really confusing. This difference between explicit and implicit. So this right here is an explicit function. Here we have chosen z to be the dependent variable, and we have chosen x and y to be the independent variables. So we say that z is an explicit function of x and y. So for example, if we write z equals x squared minus y squared, that's an explicit function. Now, you can also talk about implicit functions. So right here, this is implicit when we write it this way. We have not identified a dependent variable. We haven't identified the independent variable, so it's kind of ambiguous. So for example, let's go to two-dimensional space for a second. When you have a simple equation like a circle, so if you have x squared plus y squared equals 4, the way that sits, you would never say that that's a function, right? That's a circle of radius 2, centered at the origin. It's not a function. But what you can say is that this defines two functions of x. So there are two implicit functions of x here. Whoops, that's supposed to be an x. Two implicit functions of x. So those two functions, basically the upper semicircle and the lower semicircle, are implicit functions. They're hiding inside this relation. So remember that an equation that's just a splattering of variables and you can't isolate one of the letters uniquely, we call it a relation. So a relation is just a set of points. A function is a very specific set of points. It has to pass the vertical line test. So inside of this relation, there are two implicit functions of x. It also defines two functions of y. You could also do this. Right, there's two implicit functions of y as well. Okay, so that's kind of the idea. So let's go back up to the top. Here we go, Grant. So this is the notation that we use. There are three letters here, and you can see all three letters right there, x, y, and z. And with the implicit form, we just have basically everything on one side and a 0 on the right. Everything to the left and a 0 on the everything on the left and a 0 on the right. So that's just an implicit. So if you have some relation, it may or may not define functions. And you have to identify, do you want it to be functions of x and y, functions of y and z? You have to choose what's the dependent variable. Typically when x's and y's, we typically pick y as the dependent variable, typically, dependent on x. But you've seen, we just did a bunch of applications where we needed to choose x as a function of y. So it just kind of depends. So notationally, this is just a slightly different notation here. This is more general, right? when you have an explicit function, it's very specific. You've chosen a dependent variable and you've got an explicit form for it. If you plug in the x and the y, you get a z. Down here, it's a little more hidden. So let's talk about domain, range. So with our functions of two variables, and when you hear function of two variable, you should think explicit function. Think this way. That is the way to think about a function of two variables, like that. So z is written in terms of x's and y's. That's the best way to think of it. And the domain is now in two-dimensional space because your independent variables are x and y. Right? So you've got 2 degrees of freedom. You can go in the x direction or the y direction. So you've got a two-dimensional domain now. And so typically there is a restriction on the domain, but the domain you should be thinking now as a set in the xy plane. It's a set of ordered pairs. It's not just a set of numbers. You know, in Calc 1, when you talk about domains of functions, always, okay, well, it's some interval on the x-axis. So now we're talking about a region in the xy plane that forms the domain. And the range, like with a one variable function, the range is just a set of reals. You know, in our case, when we're dealing with a three-dimensional situation where we're dealing with a function of two variables, the range is on the z-axis. So if we have some surface up here, the range is going to be the set of z values over here on the z-axis, and the domain is going to be something down in the xy plane. So every point in the xy plane domain goes up and is, you know, corresponding to some point on the surface. So if you have a point in the xy plane, it's going to correspond to a point on the surface. So if this point right here has coordinates x naught, y naught, then this point up here will be z naught is equal to f of x naught, y naught.
Is that a projection too?
Yeah, the domain point will be a projection of that point on the surface down into the xy plane. So if you just erase the z value.
The z value is 0, right?
The z in the xy plane, the z value is 0. So in the domain, there are no z's.
Okay.
So the domain is always a collection of ordered pairs, not ordered triples.
Okay.
So then the triple part, the z part, is up here on the z-axis. So the z part, the range is going to be just a collection of z values over here. And you basically project onto the z-axis. All right, so let's talk about domain and range. So here, classic functions of two variables. These are explicit. We have z equals these different expressions. And domain, just like you did in college algebra, you basically think about what's not in the domain based on two conditions. You can't take the square root of a negative, and you can't divide by 0. So you look here. Is there any restriction here? Is there any division by 0 or square rooting of a negative? No. So here, the domain for this function is going to be the entire xy plane. So it's going to be all of R2. All of R2 for that. And if we want to know what that looks like, type it into a computer program and we can get a sense of what it looks like. All right, so this one, we have a square root function. We know there's going to be a restriction because we can't take the square root of a negative. So we know that we want to talk about the set of points that satisfies this inequality. That quantity has to be greater than or equal to 0 for the square root to be defined. We can't have any negatives in there. So then we do a little rearranging. We add x squared and y squared to both sides. I'm going to move the inequality symbol appropriately so we get that. So the set of points for which this function is defined is the set of xy that satisfies this inequality. What is the solution set then? What does that represent?
A circle in R2 with radius 5.
So that's going to be, so that solution set is going to include the boundary. It's going to be circle of radius 5 centered at the origin and everything in it, right? So the domain for this is going to be all the points inside. All those points. The domain, including the boundaries, everything. So that is the domain. The domain radius is 5. And we include the boundary. So, and what do you think this surface is? Any ideas? Subset of. So if we think about this as z equals the square root of 25 minus x squared minus y squared, we did this a lot when we were dealing with those applications where we're dealing with semicircles, opening up or down, left or right. So if we square both sides here, we should get an equation that we recognize. Isn't that a sphere? We put everything, if we put all the constants on one side. Sphere of radius 5 centered at the origin. But the condition here, so this gives us the so-called superset. So our graph is a subset of the graph of this relation. This relation is a sphere of radius 5 centered at the origin. Sphere with radius equal to 5. But the restriction that we have based on this equation is that z is greater than or equal to 0. Right? A square root is always going to be greater than or equal to 0. So we're choosing the upper hemisphere. So this will be the upper hemisphere.
So it's just the projection of like half of the sphere.
Yep.
Okay.
Right down onto the xy plane.
Just like make sure.
Step on a ball. Step on a ping pong ball. And that's going to be its domain down in the xy plane.
So does that mean that a shadow is like a domain of a function?
Mm-hmm.
Just the shape of the shadow?
Perpendicular light coming from the top. High noon is going to project down and create the domain. Yep. Exactly. So this one here, we have another square root. So we do the same type of thing. We take what's in the root, and that's got to be greater than or equal to 0 for that to work. So let's see. Any ideas? How can we solve that?
I got xy over x squared plus y squared must be greater than 0, and x squared plus y squared, it must not equal 0.
Mm-hmm. So we certainly are not allowed to use the origin, correct? So the origin is going to be excluded. So if we assume that we're not at the origin, then this is positive down here. So if we assume that we're not at the origin, so we assume that this is not equal to 0, then, so we've already excluded the origin, right? So then what has to be true is that xy has to be greater than or equal to 0. And when is xy greater than or equal to 0? Quadrant 1? Any number in quadrant 1. What about on the x-axis in this direction? Will those numbers work?
No.
No?
We're all doing
No.
0, 0.
The only place where they won't work is at 0, 0.
Alright, wouldn't stuff also in quadrant 3 be greater than or equal to 0? Negative times
Yep,
negative?
yep. Let's finish quadrant 1 first.
Okay.
So definitely the numbers on the x-axis work. So we can't choose anything below the x-axis over here. Like those are out. What about up here? Certainly those are in. What about here where y is positive and x is 0? Yeah, 0 greater than or equal to 0 is true. So we're going to get all this stuff in here for sure. And then over at quadrant 3. So we can, in fact, use these axes here. And we'll get all this stuff also. But we're not going to get this. Maybe I shouldn't put anything in there. So that will be the domain. So it's all quadrant 1, all quadrant 3, including the axes except for the origin.
So that's because they're both negative there, so they'll turn into a positive?
Yep.
Okay.
So the condition is that the product of the two has to be non-negative. So the product of the two can be equal to 0 or greater than 0. So quadrant 1, quadrant 3 plus the axes.
So it's just everything that lies along the axis y equals negative x. Just, you know what I'm saying?
Well, if we say y equals negative, all of this stuff is excluded. Everything in quadrant 1, quadrant 2, and quadrant 4
Sorry,
is
y
excluded.
equals x is what I meant. Sorry.
But it's more than just that. Y equals x is that perfect line there. It's a lot more than just that.
And also, you'd run the problem since.
Do you see?
With the origin.
Oh yeah, because if you were to move it, then you'd end up in another one.
Yeah,
You can't even do y equals x because of the origin.
Yeah, and y equals x is also bad because of the origin. Yeah, so the best way to describe this is quadrant 1 plus quadrant 3 plus the points on the x-axis plus the points on the y-axis minus the origin. Yeah, so the way we would write this mathematically, though, we would say that the domain is the set of x, y such that, and we just simply state this. That's just how we state it, you know.
When we're describing it, you want us to type that out times New Roman 12-point font double spaced, right?
Yeah. Twice.
Okay.
So usually we'll just draw a picture.
Okay.
Drawing a picture. Picture's worth a lot. All right, let's take a look at
Could you go back to that real quick?
Pardon?
Could you go back to that really quick? Didn't quite get the mathematical equation of it.
Yeah, no problem. So that's the set notation for the. All right, so the next thing that's going to help us picture some of these surfaces in three-dimensional space are things that we call level curves. So level curves, you've all dealt with them when you've looked at a map. If you look at a topographic map, it's got all those rings of constant altitude. That's what a level curve is. A level curve is a curve of constant function value. So topographical map is a really good example. So when we imagine our mountain here, if we imagine the cross section at z equals z naught, so if we take the plane at z naught and intersect, we get that circle. They call it a contour curve if the curve is floating up there on the surface. We're not really going to deal with that. We're more curious about what the projection is down into the xy plane. This is the level curve right there, down in the xy plane. So level curves are always going to live down in the domain. Curves of constant function value, they're going to be down in the domain. And so, for example, this surface right here, there's the surface on the left, there are the contour lines on the left. The level curves, though, are all projected down into the xy plane. So this is how we're going to draw them. And quite frequently, we will indicate which curve is which by indicating what the constant value is that it generates. So z1 is this plane up here, and that curve projected down is going to be that one right there. So z1 is corresponding, that one is corresponding to this ring right there. So let's try it. Let's see if we can manage to do this. Okay, so here are the instructions. We've got a very simple surface. It's just a plane. Z equals 2x minus y. It's a plane. And they say graph several level curves. So the level curves, first off, are in the domain. So the level curves are in the xy plane. And we have z. They've solved for z already. So to find level curves, we basically set z equal to a constant. We want to figure out what the curves of constant function value are, what the curves of constant z values are. So here's what I would do. I would plug the level curve in for z equals 0. So that's the constant 0. Plug in for 1. Maybe plug in for -1. So you just pick a few. So there's few. We picked a few z values. So this level curve is going to correspond to the actual intersection with the xy plane of the surface. So that will be the line y equals 2 divided by 2 times x. So something like that. So this is for the level curve z naught equals 0. So now we actually have a pretty decent idea of what the surface looks like. We know that it's a plane. We know how it's going to intersect the xy plane. So let's see. So this second level curve here, when we solve for y, we get y equals 2x minus 1. So that level curve is going to be 2x minus 1, so it's going to be just shifted down a unit. That corresponds to z naught equals 1. Okay. So is the plane above or below the xy plane right here? Is it below or above? It's above. Right, so this plane is tilted like this. It's 1 unit above right there, right? Because we set z naught equal to 1. So this is the line where all the z values are 1. So the surface is this tilted plane that's coming out of the board in this direction, 1 unit above the xy plane there.
So like it's actually like z naught equals 1 is above, like
Mm-hmm.
lifted towards our face.
Yep.
Okay.
Yep. Yep, lifted right towards your face. 1 unit out. And the other one is going to be representing the z values that are below, right? These are the z values that are below the xy plane, and we're going to get 2x plus 1. So that's going to be this line. So that's going to correspond to z naught equals -1. So those are below the xy plane. So if you imagine the xy plane like this, we now know where we're above it and where we're below it. We can kind of see that it's tilted into the board, that direction, below the xy plane there, and above the xy plane there. Right? And that's how you read a contour map. You look and you say, oh yeah, this ring is where the elevation's 10,000 feet. Right? And if you stay on that ring, you're going to be at 10,000 feet of elevation the whole time. So if you walk along this line on the surface, you would be 1 unit above the xy plane the whole time. So just like a contour map. Yeah.
Did you plan wearing that shirt today?
I didn't. But that's funny. Doesn't it? Yeah, look at all those contour lines. I had no idea. Perfect question. Perfect question. +1.
+1.
+1.
I have a question. What is
Yeah, question.
-5 plus -5?
This?
Yeah.
Yeah.
So that just means you're looking on the x-axis from -5 to 5, on the y-axis -5 to 5. So it's like a window on a calculator. They're saying just focus on that region. So essentially we want to focus, around the origin. 5 that way, 5 that way, 5 up, 5 down.
So that means your lines will not go like infinite.
Yeah.
Long.
Yeah, so they're just trying to get you to think about a smaller region. But it's funny they even say that. I mean, we're
I was worried we were going to start making cross products.
No,
And
yeah.
then
So that notation is how you do represent a two-dimensional set, though. So this says -5 by 5 on the x-axis, -5 by 5 on the y-axis. So that's getting you that 10 by 10 window. Okay, let's see our level curves here. So let's go ahead and get our coordinate system up there first. And so level curves, let's pick 0 again. That's always a good one. And if we let z be 0, square both sides, what do we get? Y equals x squared plus 1, I think. So that's going to be a parabola like that. So this is z naught being 0. Okay, so there's our surface intersection with the xy plane. Now if we put a +1 on the left side, this is going to tell us where the surface is going up. So if we walk along this right here, we're in the xy plane. So we're at a height of 0 as long as we walk along that parabola. But if we turn and jump onto this, what do we get? Square both sides, we get a 1. Looks like x squared plus 2. So now our level curve is a little bit higher. So that's z naught equals 1. So that's above the xy plane. So you're imagining kind of like a cave. Here we're at a height of 0, and we go this direction. Now we're at a height of 1, so it's kind of a cave. Now let's check -1. -1. 0, no solution. No solution. Right? Positive square root can't be negative. So this surface does not go below the xy plane. It's totally above the xy plane. And it's opening that way. So it's kind of like a, kind of like a cave. Let's graph it on, just graph it on GeoGebra and take a quick look, see if we can manipulate it. Oh, I already. Let's see, it's live still over here. Can somebody tell me what that was again?
Z equals square root of y minus x squared minus 1.
Z equals square root of x minus y squared minus 1. 1/2 power. Oh, wrong. X minus y squared. And then it was -1 in there?
Mm-hmm.
And that was the square root, right?
Yeah.
So,
But the x was squared, not the y was squared.
oh,
Yeah.
x is squared?
Yep.
And the y is not squared?
Y is not squared.
Wow, look at that.
What? And I'm pretty sure it's positive y negative x.
Yeah.
What?
Yeah. Yeah. Y minus x squared
Y minus x squared minus 1. So y.
We can do this.
Good grief. Where's copy and paste when we need it?
Yeah.
Right, so there's what we kind of thought we were going to get. So we get that surface. Pretty cool.
I like it.
Yeah, it's nice having a 3D grapher because it gives you, a good sense of what's happening.
So how do you know when it like stops?
Stops. It goes on forever.
But like oh, it keeps getting
Yeah, so the
taller?
cave keeps getting taller.
Oh.
Yeah, yeah. So it's a hard cave to get into.
Yeah.
It's a long walk around to get into the opening. All right, so, but that gives, so these level curves can give you a real, once you play with them a little bit, you can get a pretty good sense of what the shape looks like. Maybe trying to draw that shape in three-dimensional space is hard, but you can at least get a sense of what it looks like. Definitely get a sense of what it looks like. Wait, is that the last slide already?
Yeah, that's that one's
All right, I'll give you some other ones. All right, so try this one. So find the level curves for z equals x squared minus y squared. All right, so do the level curves for that function. So when we talk about level curves, it's always for a function. When we talk about traces, traces could be for a relation. It doesn't have to be a function. So like those ellipsoids are not functions, but they have traces. They intersect the xy plane, they intersect the yz plane, they intersect those coordinate planes.
For what domain do you want us to do that?
Oh, just do it kind of near the origin. You know, not, we'll always focus right around the origin. Figure out what the stretch is. Oh, I figured it out. All right, so if you're trying to stretch one axis on GeoGebra, you place you hit the shift button first, and then you go to an axis. And And that's really cool that you can just do one axis. So shift button. Shift. Shift first. All right, let's take a look at our three traces. Okay, so for our level curves,
There we go.
if we pick 0, what is that level curve?
Y equals
Y
X.
equals X?
No.
Wrong.
Root X? Plus minus X.
It's more than just y equals x.
Y equals plus minus?
Yeah, y equals plus or minus x. So you should get intersecting lines.
Yeah, so that'd be an X.
Intersecting lines. So the intersecting lines are corresponding to a height of 0. So this is where your surface is intersecting the xy plane. So if you're walking along your surface and you're sticking to that path, along here, turn and go along there, you have no elevation gain. All right. And then if we go to up to the next one, so this was z naught equals 0. We go z naught equals 1. That gives us a sense of, okay, which direction do we go to get above the xy plane? Which way are we going to get up? So x squared minus y squared is 1. That is a hyperbola with x-intercepts and not y-intercepts. So that would be this direction. All right, so that corresponds to z naught equals 1. So you head right or head left, and you're going to go up. Now let's plug in -1, see if this thing goes below the xy plane. And of course, we just turn it into the standard form for another hyperbola. This one has y-intercepts, not x-intercepts. So that's going to correspond to z naught equals -1. So that tells us if we're standing at the origin, and we head in the positive, this is y, this is x. We head in the positive y direction or the negative y direction, it's down. Head in the positive x direction or the negative x direction, and it's up. That makes sense?
Can we graph this? I kind of have a hard time visualizing what this would look like.
So what is this surface?
It's a saddle.
Saddle surface. So,
A
and
normal
now
monkey saddle.
one question that we will be talking about, if you are trying to go to the summit in the shortest distance, what should your relationship to the level curves be?
Very dense.
Perpendicular.
Oh.
Right? If you want to get to the top fastest, you're going to go perpendicular. Like if you look at a topographic map, you're going to go perpendicular. If you're going to get to the summit, the shortest distance is just going to go perpendicular to your level curves. So perpendicular to level curves. So if we do this one, z equals x squared minus y squared. And then let's go back to the standard window. And so zoom in. I guess I'll go that way. Too far.
I think we broke.
Good. All right, so you can see the saddle there. It doesn't like these saddles though. I'm not able to rotate it very easily. A lot of rendering, I guess. But you can see.
You tried adding
Oh yeah, I wonder if that would make it simpler. I don't know how you do that in 3 space yet. We should play with that.
Could you just scale the z-axis and make it shorter?
We should be able to. It's not moving right now though.
Maybe you need that like hand tool
Oh, there
on
it
the
is.
side.
So if we come down.
There you go.
Just, yeah, this computer is kind of wimpy. I'm sure in your home computer it probably does better than this computer. But you at least get the sense of what it does and how it works. Pretty cool.
But what about the sun?
Well, that one goes up forever.
Well, like, what were you saying though?
So these level curves here are going to be like that. They're going to be more hyperbolas, more and more hyperbolas. So if we want to go towards this, if this ended, we would go we go this direction, perpendicular to these level curves to get to the top fastest. Now this one's a little funny because it's got up this direction and it's up this direction. But if you go perpendicular to the level curves, you'll go to the top the fastest. All right, let's try another thing. Let's do, so determine which quadric this is. Quadric, not quadrac. Quadric. So let's suppose we have x squared minus y squared minus z squared equals 1. Figure out what quadric that is. So 3 traces. Identify each of the 3 traces.
Is it a hyperboloid in 2 sheets?
Maybe. What's your xy trace?
X twice is x squared minus y squared equals 1.
What's that?
It's a hyperbola.
Hyperbola. Next trace.
Another hyperbola.
Next trace.
Another hyperbola.
No!
Y squared plus
Negative
z
and a
squared.
negative.
No!
Y squared plus z squared equals -1.
So what is that?
Non-existent.
Empty. Right? Yeah. So
There's
here,
no negative, it's a
Yeah, you
negative
can
that
never have the
equals
sum of 2
positive.
squares being a negative number.
sum of 2 squares being negative means empty set. So we have a hyperbola. So the one that was the empty set is if x was 0. So that's the yz trace. So that one's empty. So we have 2 hyperbolas. And the empty set. So this is going to be the hyperboloid of 2 sheets. Yeah. So that one right there, super common, even though it's in some ways the simplest trace, that's the one that most people get wrong. So you've got to be super careful with that because you're dealing with this equation, y squared plus z squared equals -1. So that's the one to be most careful on. Yeah.
And we know it's empty because it's just like that. Is that the reason why?
So it's empty because there's no ordered pairs that satisfy that equation. Right? There's no way a sum, the smallest y squared could ever be a 0, the smallest z squared could ever be a 0. So there's no way to add a sum of squares and get a negative number. Right? So there's no ordered pair that satisfies that, so it's the empty set. So that corresponds to the hyperboloid. Hyperboloid of 2 sheets is the only one that has a cross section with nothing. Right? The cone has a cross section that's a point. The paraboloid has a cross section that's a point. The hyperboloid of 2 sheets is the only one that's disconnected.
Are we eventually going to get to the point measuring the distance between the hyperboloids?
Say that once again.
Are we ever going to be measuring the distance between the
No, the 2 bowls?
Yeah.
No.
Okay.
No. We could, but we won't do it.
That's why we
I'll
hire
skip the extra
mathematicians.
Yeah, there's not extra
But
credit on
isn't that
that.
essentially what we're doing in the spinning cube?
Finding the,
Because we're finding the distance between 2 planes, and those planes are at the ends of the things, and that distance is that.
finding the distance between those 2 planes is going to be really important. Yes. And then the weird thing about the cube is that it takes one edge. If you take this one edge and you rotate that about this axis, so skew lines, if I take that skew line and wrap it around that, it create that one segment that's skew, one segment creates that whole middle region. So that one segment skew to the axis, when it rotates, it's going to create that curved region, which looks like a hyperboloid of 1 sheet. Yeah. All right, let's pause until Monday.
Nice.
See you on Monday at 1 p.m.
So when is the thing? On Thursday, the next
Module? A week from today. A week from today, finding 2 planes.
We actually, like, we
That's
just
when
gonna
it's
bring it,
due?
like, We don't need to bring.
You don't need to bring anything except for, so you can either email it to me if you want to, if you like typing on Word or something, you can just email it to me instead of bringing in a hard copy.
Would we
Totally
be,
up to you.
would we be able to send you a PDF or something?
Yep,
Okay.
yep, totally fine.
Are we doing this solo or is this with a group of people?
No, you can do it solo. You can work with each other though.
Okay.
Totally fine. Everyone turns in their own, but you're more than welcome to collaborate.
Okay.
Yeah, totally fine. All right, see y'all. Have a good weekend. You don't collaborate?
Oh my gosh.
You guys are gonna collaborate? I'm so surprised.
I've only known each other for a while.
So do we just get to show you the equations for it, or?
Yeah, so you'll just turn in the equations for the two planes. The equations for the two planes.
Have you graded my thing?
Your exam? I did.
Did I do bad?
No,
Did I do like okay? Or did I do actually?
I can't remember exactly. If I had to, do you want me to guess the letter?
Yeah.
I think it was a B.
I love this subject.
I think it was like an 86.
Okay.
That's what I'm thinking. I'll put it in there right now. When I go back to my office, I'll put them in.
I just looked at your email today for that quiz. Can you still extend it or no?
Now what is it? We can do it till tonight.
Okay. So I can do it like right now.
Yes.
Okay.
I'll do it.
Thank you.
You're welcome.
Mr. Boss.
Yes.
So with the quiz, I accidentally like rounded it to the wrong decimal, and I was so mad about it.
Are you gonna email me?
Yeah, I will.
I'll email you. I'll give you credit.
Okay.
Yeah, if you just rounded the wrong decimal point, that's no big deal.
I mean, it was really lame, and I was like, oh.
Yeah, I mean that's totally fine.